everyone. So I want to switch gears and talk about the next part of this unit, which is the gravitational forces. Now, this may not seem like it's going to play a factor with what we were just talking about with circular motion, but trust me, it does. So, the first thing that I want to remind you guys is the law of gravitation. We haven't actually talked about it too much. I think I briefly described the idea about it. For example, it was brought up by Newton. He was kind of the one who coined the term gravity. In fact, in his pursuit of this law of gravity, trying to explain why objects fall the way they do, he actually developed the basis of Newton's three laws of motion and calculus. So he basically made strides in two amazingly tough fields of science and math simply just to explain why objects fell. Um, he realized through experimentation that all masses end up attracting other masses, regardless of size or anything like that. And he ended up coining this a gravitational force. Now, it turns out that this force is the weakest of all the other forces. I had mentioned in my intro to forces topic that all the forces that we've talked about, tension, frictional, applied force, normal force, all of these forces could be categorized into one of four categories, which we call the fundamental forces. There's the gravitational force, which is the weakest of them all. Then there's the electrostatic force, the strong force, and the weak nuclear force. So this is an extremely weak force because, for the most part, the only time that it actually becomes noticeable is once we get to the celestial object size. Essentially, what I mean is we have to get so massive to the point where we're a very large asteroid, a dwarf planet, a moon, a planet, a star, a galaxy, a black hole. Once we get to a very massive object, that's when we actually start to experience or be able to measure any form of gravitational force. But technically, any object has it. So this is actually the reason why it's one of the weakest. So again, through the experimentation of Newton, he found that the strength of the gravitational force was directly proportional to the value of the masses. So if the value of the mass doubled, so did the gravitational force. He also found that the strength was inversely related to the distance squared, meaning that if you doubled the distance, the the force didn't just go down, but it was squared as it went down. It went down by four essentially. Now the equation that he ends up coming up with is this: Fg equals g m1 m2 over r squared. This is what I like to coin the big G equation. Two terms of note: the big G uh, refers to the universal gravitational constant. So this is a constant that's true all throughout the universe. Don't confuse this with the little g, the value of the acceleration on Earth. One thing I want to bring your attention to is this unit. So this kind of looks like a gross unit, and on the AP reference table, this is the unit they give you. However, if you look over at the Regents reference table, you'll see a slightly different unit, which is Newton meter squared per kilogram squared. Now they're the same unit. It's just that this foregoes the newtons and replaces it with the per kilogram seconds. Sorry, meters kilograms uh, per second squared. That should be squared. All right. And then the other thing that I actually want to point out is this: R. R does not stand for radius, and I'm going to make sure to stress this in the later part of this video, not in this video, but in one of the later videos. But R stands for the distance between centers, and this is actually an extremely important concept. It is not the radius; it is the distance between centers. Now, one thing that's nice about this is that the size of the planet doesn't seem to matter. According to this, the only thing that really matters is how far apart the middle of the two masses are. Essentially, we could take like if we had the Earth and the Moon, we could take them and condense them into an infinitely small point in space, where all of its mass is located in that one spot, and the force of gravity between the Earth and the Moon would not change. In fact, if you took the sun and you somehow turned it into a black hole of equal mass, and you put it in that same spot, it would turn out that gravitationally, none of the planets would change. They would continue their motion as if the sun was still there, and not a black hole. So the size of the object doesn't really matter as long as the mass stays the same and the distance between the centers are the same. So again, if this was my diagram, if I ballooned the Earth up while keeping its mass the same, as long as this center was still there and as long as the mass was still m, I would still have the same exact force between these two objects. One of the things to point out is how this force compares. So we actually know the how the force that the Earth exerts on the Moon versus the Moon on the Earth compares. Because of Newton's third law, we know they have to be equal. So if the Earth exerts a force of F on the Moon, then the Moon exerts that same force of F on the Earth. However, if we actually look at the equation, it makes a lot more sense because we can see in the equation that this also has to be true. I probably should have put this as big M and little m. So looking at this equation, we have big M as the mass of the Earth and little m as the mass of the Moon. Well, it doesn't matter the order that I put M and M because as long as I'm multiplying it, I always get the same number. 3 times 2 is the same as 2 times 3. So because of that special property of multiplication, always being the same thing, we end up getting the exact same force regardless of which mass we put first. Now, there's one thing to recall is that we actually already have an equation for the force of gravity. It was Fg equals mg. Now, this was true for like being on a planet, but now we have a more general equation for the force of gravity between two objects. Well, what this means is I can actually take these two equations and set them equal. Um, and what this will do is that this will get me the gravitational acceleration uh, on a planet at some point. So I set the two equations equal and end up getting this slightly altered version of the force of gravity equation, which refers to the gravitational acceleration on the planet. If this r is representing the radius of the planet, then this is actually telling me the acceleration on the surface of that planet. So, for example, if I want to put in the moon's radius into this equation and the moon's mass, that will tell me how fast the objects on that planet are going to accelerate, or not planet, sorry, moon. How fast objects will accelerate on the moon. So just keep that in mind that we have this slightly altered equation. Now this is not on the reference table, but it's fairly easy to derive. So there's no need for it to be on the reference table. Now, I'm not going to actually do any practice questions using these equations because for the most part, it's really standard. It's, plug the numbers in, chug out an answer, easy enough. I want to talk about the more complex aspects of this equation. And that leads me into this method that I call the 1-1 method. Basically, what's going to happen is every now and then you're going to see a question where instead of telling you the numbers to calculate something, they're going to tell you a before and after scenario where they'll say you're comparing like a moment where you're some distance apart from something, and then you'll compare it to another point where you're further away, or maybe you're closer together now. And they want to see how the force changes. So they'll mention about how some variable changes, like distance or the mass, and then they want to know how the force changes. Or maybe you're comparing the force of gravity that you experience when you're on the Earth versus the force of gravity you would experience on Jupiter. Instead of giving you Jupiter's values, though, they will give you a comparison to Earth. Say that Jupiter is 500 times the mass of Earth and it has a radius that's 10 times the radius of Earth. With that information, we would be able to figure out how much we would weigh on Jupiter based off of how it relates to Earth. Um, so there's a bunch of different ways that you could do it. If for some reason you don't like the 1-1 method, technically one method that you could use is that you just make up numbers for all the things that they don't tell you, do the calculations, and then compare the two your two answers. You have to do the before and after, but this cuts down on that work tremendously. So the way it works is that you find the equation you're supposed to look at, based off of what things are changing. You plug a 1 in for every variable that stays the same, and then you plug a number in for whatever's being changed, and you plug the number that relates to what factor it's changing by. So, for example, if they say that it's doubled, that means that it changes by a factor of 2. If it got quartered, changes by a factor of 1/4, and so on and so on. And then from here, I can figure out how much my new variable is going to be compared to the original. So I'm not using real numbers. None of these numbers should have units because it's a ratio essentially. All right, so try that with this. So pause the video, work itself, and we'll go over in a second. All right, so they tell us here that the distance between the particles is doubled, and they want to see how the gravitational force between them changes. So based off that, I'm going to start with my first equation, Fg equals gm1 m2 over r squared. The G, the M1, and the M2 all stay the same because it doesn't. G is always constant, and they don't say anything about their masses changing. The only thing that changes is the distance. It got doubled. So I'm going to do 1 times 1 times 1 over 2 squared. That gets me 1/4, 1 over 4. And again, that does not mean that my force of gravity is 0.25 newtons. It means it's 1/4 of the original force. So I can say that Fg ended up getting quartered. And that's kind of what I said earlier before, that, because the inverse square relationship between force and distance, I end up seeing that if I double the distance, I quarter my force. Here's the next one. Pause the video, work itself, and we'll go over in a second. All right, so this one's actually a really tricky one for both parts. The first part is tricky because it is very simple. It's m. Uh, just because I displace something doesn't mean my mass changes. So mass never changes unless I physically change the object. If I'm just moving it to a different location, the mass won't change. Now, for part B, the weight will end up changing. So I'm going to have to actually go back to the Fg equation and use the 1-1 method for that. So I start with the equation gm1 m2 over r squared. Once again, everything up top stays the same. Now, what makes this difficult is what do we put in for r? Now, I'm going to just say what it is now, but I'll show you the diagram that kind of shows it. So it tells us that it went up an altitude, that's a key word here, an altitude that's twice the radius of Earth. That means that my distance actually tripled. So I do 1 times 1 times 1 over 3 squared. That's 1 over 9. So in terms of W, I would say that it's 1/9 of W. All right. Now, this is the diagram that I want to show that kind of shows this. So on this, we were originally on the surface of the planet. That means that we were originally a distance r from the center. Because remember, r doesn't stand for radius, it stands for distance between centers. When I'm on the surface, I am a distance r from the center. When I go to an altitude, which is measured from the surface, of 2r, that my distance to the center is 3r. So I go from r to 3r. Therefore, that's why I ended up getting 3 before, and that's why I ended up getting 1/9. All right, here's the next one. Pause the video, work itself, and we'll go over in a second. All right, so again, this is another example where I could use the 1-1 method. Instead of doing a before and after of two scenarios, I'm doing a comparison between Pluto and Earth. and every measurement I'm being told is relative to the Earth. So I use the equation for the acceleration of gravity on Pluto, g m over r squared. I plug in the 1 over 500 for the mass and 1 over 15 for the radius. And I end up getting that the answer is 0.45. And again, this is times Earth's acceleration of gravity. Plugging in 10 for Earth's acceleration of gravity, I end up getting that the gravitational acceleration on Pluto is 4.5 meters per second squared. All right. And then we'll do this one. Pause video, works up. We'll go for a second. All right. This one's a little bit trickier. So first, you'll want to draw it out. Now, I put in x and r minus x because I was originally going to do a slightly different method, but instead I'm actually just going to say that this distance is RA and this distance is RB. All right. There actually is a few different ways, but this is the one that's definitely the easiest for me to explain and the easiest for me to write down. So because I know that the force on an object at this point P is going to be equal to zero, I know that that means that the force of gravity acting on the object has to be equal to each other. I know this because if I put a point here and I draw my FBD, one force, the force caused by object B, is going to pull it to the right. It's going to attract it to the right. Object A is going to attract it to the left with the force Fa. And because of Newton's laws, if this sum of the forces equals zero, these two forces have to equal each other. So I can set the equations equal. Mx and g are on both sides. They're the same. So now I have this. Ma they said was just m, and then mass of b was 4m. So I plugged that in, and now I once again have an m on both sides that I can cross out. And then I'm going to cross multiply, and I end up getting this: rb squared equals 4ra squared. I have a perfect square, so I can square root them. So what this tells me is rb equals 2ra. Now, you might think that this means that the point is directly in the middle, but it's not. I'm not done yet. So going back to the original question, it says that A and B are separated by a distance r. That means that the distance, based off of my labeling, that if the distance between A and B is r, then RA plus RB has to equal r as well. So I write r equals RA plus RB. I know that RB is equal to 2RA. So I plug that in and I get that the total distance is actually 3 times the distance between A and P. With that, I can solve for RA and I get it's equal to a third of R. Again, that actually makes sense because if this distance, let's say this distance was, or actually let's go with this one, this distance was 2 meters, then because of this relationship, RB would have to be twice that at 4 meters. And that is 2 meters is 1/3 of the total distance of 6 meters. All right. All right, so I'm going to leave it here for now. There's one more thing that I want to talk about with the 1-1 method, but for now, I just want to end with the easier one. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.